Hi, this is Gio with the course Signals and Systems 2 at UPF in Barcelona. This is class number 12. Check my webpage or get in touch via email if you have any questions. In the last class, we learned how to represent a continuous time signal by its samples, which are its values at points equally spaced in time, and then reconstructing the original continuous time signal from its samples. We also learn under what conditions such reconstruction is possible without losing information. Such conditions are given by the sampling theorem. Today we will talk about communication systems. They play a key role in our everyday life, and many of the concepts we have developed throughout this course are essential to analyze and design communication systems. A full study of communication systems would require not one but several courses on its own, but at least today we will introduce some of the basic principles behind them, such as the concepts of modulation, demodulation, and multiplexing. So modulation is embedding an information-bearing signal into a second signal. So imagine you have a signal that carries your information, which could be anything, a song, an audio file, a voltage, and you want to transmit it. Through modulation, you embed such information into another signal. This other signal is the one that will be used to convey the information at a certain receiver. The objective is producing a signal whose frequency range is suitable for transmission over the communication channel to be used. For example, voice signals are in the range between hundreds and thousands of hertz, whereas a microwave link may require signals between hundreds and thousands of megahertz, million times as much. Think about Wi-Fi, which works at 2.4, 5, and soon also at 6 gigahertz frequencies. So to transmit a voice signal over these channels, we must shift it to a higher range of frequencies by modulation. Demodulation is basically the opposite operation where we extract the information bearing signal from that second signal that was carrying the information. Multiplexing, instead, consists in simultaneously transmitting multiple signals with overlapping spectra. So multiplexing in frequency can be useful, for example, if you and your friends would like to share a wireless connection. So a Wi-Fi access point is capable of allocating each of you a different portion of the available spectrum, transmitting all of your signals simultaneously and allowing you to recover your own signal only by looking specifically at your portion of the spectrum. We will see an example of multiplexing towards the end of this class. In what follows, we will introduce one possible and simple way of performing modulation, which is sinusoidal amplitude modulation. So let's imagine that our information-bearing signal is x of t. X of t carries all the information we want to deliver at some receiver. As I said, we use a carrier signal to take this information somewhere else, and the carrier signal, we call it c of t, is simply a cosine of omega ct plus theta c, right? Omega c is what we call the carrier frequency. We'll see that omega c is the frequency at which our information bearing signal will be shifted. So it's usually a very high frequency. The modulated signal y of t is obtained as the product between x of t and c of t, a simple product in time. It's what you see represented at the bottom right in the figure. So x of t is multiplied by cosine omega ct plus theta c and produces y of t. Y of t is the modulated signal, x of t is the modulating signal or the information bearing signal, and the cosine is the carrier. Great. What about their respective Fourier transforms? So if the information bearing signal, also called the modulating signal, has Fourier transform x of j omega, and the carrier has a Fourier transform C of j omega, then the modulated signal, being it the product between x and c in the frequency domain, will be the convolution between capital X and capital C, apart from a factor 1 over 2 pi. Let's now take a closer look at what happens in the frequency domain. So again, our information signal has a spectrum x of j omega. Let's assume that this is the one represented at the top right of this slide, okay? It's between minus omega m and omega m, and it has a certain shape. For example, the one illustrated in this slide. Then our carrier signal is a cosine signal, as we said before. For example, when the phase theta c is 0, it simply reduces to cosine of omega c t. The Fourier transform of cosine omega c t, we know, is given by two impulses, and it's pi times delta of omega minus omega c plus delta of omega plus omega c. So it's two impulses centered at frequencies plus and minus omega c. We see this represented also on the right, c of j omega. So when we modulate our signal, we obtain in the time domain that y of t is the product between x of t and the cosine of omega c t, and correspondingly in the frequency domain we obtain that y of j omega, the spectrum of the modulated signal, is 1 over 2 pi times the convolution between x and c of j omega. But we recall that doing the convolution between a signal and an impulse corresponds to shifting the signal. In this case, there are two impulses at plus and minus omega c, so the result of this operation is shifting the spectrum x of j omega up and down at frequencies plus and minus omega c. So we have two replicas that are created of our original spectrum. They are centered around plus and minus omega c, as you see in the figure at the bottom right. Notice that the original spectrum is still there, and it's possible to recover it. There hasn't been any overlap, there hasn't been any distortion. This as long as those two replicas do not overlap, which, if you look closely, is the case if omega c is larger than omega m, because that guarantees that the two replicas are bounded away from 0. This in practice will be the case because, as we said at the beginning, the purpose of modulation is to transfer a certain information, which is contained at lower frequencies, up to omega m in our case, to a higher frequency, omega c. In the examples I gave you about the radio channel, this omega c is much larger than omega m in practice. Let's now see how to demodulate a signal after we have performed sinusoidal amplitude modulation. So let's talk about sinusoidal amplitude demodulation. What we will consider here is what's called synchronous demodulation. It's called synchronous because, as you see, we will assume that we have knowledge of the carrier used by the transmitter. So what we do here to demodulate is actually multiply again by the same carrier. Remember that when we modulated, we multiplied our information signal by a carrier. Well, here at reception, when we do demodulation, we simply multiply again by the carrier. So we take the signal y of t, which is the modulated signal, and we multiply by the carrier. Then we will have to apply a low-pass filter. So let's see this in pictures. Let's look at the figures on this slide. So at the top right, we have a representation again of the spectrum of the modulated signal. It's the one we saw on a previous slide. So again, because we are multiplying by the carrier, here we have plotted the spectrum of the carrier. Again, it's the two deltas centered around omega c and minus omega c. When we multiply y by the carrier c, again, in the frequency domain, the corresponding result is a convolution between their Fourier transforms. So what that produces is the spectrum of y of j omega replicated twice. First, shifted up everything by a quantity omega c, and shifted down by a quantity minus omega c. The result, the superposition of those two replicas, is given at the bottom right of this slide. So as you see, this operation creates some replicas at high frequencies because the spectrum of y, which was around omega c, goes up to 2 omega c and down to 0. And the other one, which was around minus omega c, goes up to 0 and down to minus 2 omega c. The result is the W of j omega that you see at the bottom right. So there are two replicas at very high frequency, around 2 omega c and minus 2 omega c, and the two replicas have perfectly overlapped around the origin to create the original spectrum, basically, between minus omega m and omega m, apart from a scaling factor 1/2. So in order to recover the original signal x of t, the original spectrum, we simply have to apply a low-pass filter around that part of the spectrum, the one that you see boxed in a dashed line. We can see the same thing in the time domain. So now we have represented the same operation and we've done some calculations to appreciate what happens when we demodulate synchronously. So the signal W of t is the one we obtain by taking the modulated signal y of t and, as I said, multiplying again by the carrier. We're using exactly the same carrier that was used to modulate. So the same frequency omega c and the same phase theta c. So cosine of omega c t plus theta c. We recall that y of t was x times the same cosine. So W will be x times the square of the cosine. Square of the cosine of omega c t plus theta c. We know that the square of the cosine is equal to 1/2 plus 1/2 a cosine at double frequency, and therefore we have the result at the top right of this slide. So W of t, the recovered signal, would be half x of t plus half x of t cosine of 2 omega c t plus 2 theta c. The first of these two terms is basically the original signal, just scaled by a quantity 1/2. The second one is a signal at a very high frequency, a frequency 2 omega c. Recall that the carrier was at frequency omega c. This is a double frequency. So I say that after doing this, we will apply a low-pass filter. What happens when we do that? Well, the low-pass filter will keep the first of those two terms, which is the original signal. It will be kept by the low-pass filter. But the second one, which is modulated at twice omega c, a very high frequency, will be filtered out. So looking at the system diagram at the bottom, we have at the bottom left, again, the process of modulation. So we have a signal x that carries our information. We multiply by the carrier, cosine omega c t plus theta c, and we produce y. Then, to the right, we have the demodulation. We get y of t, for example, somewhere else, after having transmitted y of t over a wireless channel. Then we multiply y of t by the same cosine, by the same carrier, with same frequency and phase. We obtain W. We filter W with a low-pass filter that eliminates the high frequency component and gives us back the original signal x of t. What happens if we are not synchronized with the carrier? Notice now the difference at the bottom of this slide. Now, when we do demodulation, we don't multiply by the same cosine of omega ct plus theta c, but rather by a cosine of omega ct plus phi c, a different phase. So now let's look up at the top of the slide. This time, once we multiply y by a cosine that has phase phi c, the result will be half x of t cosine of theta c minus phi c plus half xt cosine of twice omega ct plus theta c plus phi c, right? Again, we apply a low pass filter. The second component, the one at very high frequency, twice omega c, will be filtered out. And what's left is half x of t cosine omega c minus phi c. The factor 1/2 can be compensated, but we have a remaining factor cosine omega c minus phi c. So this is what we will recover at the end. Now, if the oscillators in the modulator and the demodulator are in phase, so when theta c is equal to phi c, as in the previous example, then the output of our low pass filter will be exactly x of t, exactly the original signal. But notice that if the oscillators have a phase difference of half pi, for example, so if theta c minus phi c is half pi, then the output is actually 0. So in general, to have a maximum output signal, the oscillators should be in phase, theta c equal to phi c. But even more importantly, the phase relation between the two oscillators at the modulator and demodulator should not change over time, so that the factor cosine of theta c minus phi c, whatever it is, does not change over time. Indeed, if that factor is constant, then the recovered signal, the demodulated one, is just a scaled version of the original signal. So we're happy, I'd say. However, if that factor changes over time, pre-multiplied by x of t, it produces a distortion, and the demodulated signal may differ significantly from the original one. Note that keeping a constant phase relationship requires a synchronization between modulator and demodulator, which are usually geographically separated, since I may want to transmit something between two different points in space after all. Typically, the available spectrum for transmission is broad enough to accommodate several signals simultaneously. Think about the radio, which can accommodate several channels at different portions of the spectrum at different carrier frequencies. The different voice music signals have spectra that overlap in frequency, but they can be shifted in frequency through modulation, such that each occupies a different non-overlapping portion of the spectrum. Then they can be transmitted simultaneously. This concept is referred to as frequency division multiplexing and is the basis of many communication systems. So let's imagine the scenario represented on this slide. We have three different signals, xa of t, xb of t, and xc of t. These signals each carry different information. Their spectra in general overlap, but they can be shifted to different frequencies and transmitted simultaneously such that they do not overlap when they are modulated. So this is what we do here with frequency division multiplexing. So we take the signal xa of t, we multiply by cosine omega a t, so we modulate at frequency omega a, we obtain what we call ya. For xb of t, we modulate at frequency omega b by multiplying by a cosine of omega bt. And for xc of t, we modulate at frequency omega ct, and so on and so forth if we have more signals. Then we sum everything up and we transmit over the medium w of t, which is the sum between ya, yb, and yc. Let's look at the spectra of these signals. So let's assume that, as represented on the left of this slide, xa, xb, and xc have that particular shape for their Fourier transforms, for the spectra. It doesn't really matter, it's just an example. So notice that each has a different shape, but they all occupy the same portion of the spectrum, between minus and plus omega m. Right. However, after having modulated them, so looking at the right part of this slide, xa becomes ya, and ya sees the content of its spectrum at frequencies plus and minus omega a. Similarly, yb sees the content of the spectrum at frequencies plus and minus omega b. and yc has the content of the spectrum at frequencies plus and minus omega c. So if omega A, omega B, and omega C are properly chosen, if they're well separated, then when we transmit YA, YB, YC, their sum, their superposition all together, we obtain W of j omega, which is at the top right of this slide. In W of j omega, all the original spectra, all those different shapes, are present and they are separated because the signals have been modulated at different frequencies. But how to recover one of these signals? For example, XA of t. Well, we need two basic steps. First, we will need bandpass filtering to extract the modulated signal that corresponds to a specific channel. For example, signal A. So if we use a bandpass filter to recover what corresponds to signal A, we would take the content around omega A and minus omega A and filter out everything else. Then we need demodulation to recover the original signal. Recall that demodulation means remultiplying by the same carrier, in this case omega A, and low pass filtering. So here we see the operations I have just described in a system diagram. So if, for example, we want to recover XA of t from that signal W, which was the sum of all the modulated signals, we need to bandpass filter first. So with the bandpass filter represented on the left of this slide, we cut out everything that corresponds to signals XB and XC, and we will only be left with what corresponds to signal XA, which is at around frequencies omega A and minus omega A. This is called demultiplexing. We are basically untangled everything. We are extracting that signal that is of interest to us. Then after that, we do demodulation, as we saw previously, earlier in this class today. So multiplying by cosine omega A t, because the signal we're interested in has been modulated at frequency omega A, and then apply a low pass filter to recover the signal XA of t. So today, to wrap up, we talked about basic communication systems and how some of the concepts we have developed throughout this course, such as the Fourier transform, the convolution, and the relationship between time and frequency domain, are essential to analyze and design such communication systems. We learned about basic concepts and operations like modulation, demodulation, and multiplexing. In the next class, we will introduce the Laplace transform, which is a generalization of the Fourier transform. The Laplace transform is necessary to study the behavior of a broader class of systems, for example, systems whose impulse response does not admit a Fourier transform can still be studied through the Laplace transform. See you in the next video.